Hello, my name is Przemysław Koprowski, and in this video I will talk about functional composition. I will present how functional composition can be used to obtain some interesting visual geometric patterns called shaders. This video is nothing else but an English version of my talk that I gave for the Day of Pi 2022 at the University of Silesia. I said that I will talk about functional composition. But first of all, in order to understand what a functional composition is, we must know what function is. I believe that some of you has already encountered the notion of function. Some of you well know what the function is, but for those of viewers who are not familiar with the notion of function, mathematical function can be viewed as a kind of a machine or factory or a device that takes some input and produces some output. Of course, this input and output can be quite arbitrary. In general, we can imagine a machine that takes wood planks and produces furniture. This is a function. As long as always from a given wood plank it produces the same furniture, it is a function. However, for working in mathematics, it's more convenient to consider a function that uses and works on mathematical objects like numbers. For example, the machine that you see on the screen right now takes numbers and produces their square roots. We can also consider other mathematical objects, for example vectors. We can think about a machine, a function that takes a vector and produces the length of the vector. So the input for our function is the vector and the output is its length. How such a function can be built? How can we construct a function that computes the length of a vector? So suppose that we have some two-dimensional vector. This vector has two coordinates, xv and yv. So the xv is the horizontal span of this vector, while the yv is the vertical span of the vector. So we obtain a right triangle, and the Pythagoras theorem says that the length of the vector is just a square root of the sum of squares of the two coordinates. So the length of a vector v is the square root of xv squared plus yv squared. So our first function, I will call it length. It takes a vector v given by its two coordinates xv and yv and returns the square root of the sum of the squares of xv plus yv, which is the length of the vector v. So let me now visualize this function. We want to see how this function looks like. To this end, I will implement this function as a shader using special language, OpenGL shading language, GLSL. We can do it on a dedicated web page called Shader Toy. This page contains lots of shaders, and anyone who is watching this video can open this page without even logging to and try to build a shader himself. You can repeat the steps that I will do in a moment and see yourself that it actually works. The page is available at the www.shadertoy.com. In order to create a new shader, we need to click this button at the top right corner, New. This opens a new page where we can implement our shader. The code of the shader is in the window on the right part of the screen, and the result is visible in the window on the left part of the screen. when we start a new shader, some code is already there. There is an example shader available by default, and the result of this default shader is visible now. It consists of some changing colors on screen. I will stop the animation because we don't need it right now, and I will change the code of the shader here. I will just erase most of that, and I will increase the font size so it will be easier for you to read on screen what I'm doing. So I will switch to a bigger font, and I will erase actually everything from here to here. I will leave only the last line that I will explain in a moment. So this is the function that we want to write. This is the function that we want to visualize on screen. This function takes a single argument, which is a vector. This vector is called frag_chord, and it outputs also a single value. This value is a color. It's called frag_color. First of all, before I visualize the len function, I will first show you how to display any fixed constant color. The color is given by 4 coordinates: RGBA, red, green, blue, and alpha, which is opacity. All 4 coordinates vary from 0 to 1. 0 is the minimal and 1 is the maximal value. So if I put 3 zeros here, 0, 0, 0, and 1 as opacity, and I'd click this little triangle in the bottom left corner of the editor, then we obtain the black window. 0, 0, 0 means 0 red, no red at all, 0 green, no green at all, and 0 blue, no blue at all. So this means we have a black color. The last coordinate is the opacity, which I will fix, and I will keep it fixed at 1, because even if I change it in this case, it will not do anything, because there is nothing behind this window. Of course, behind this window there is all the electronics of a screen, but of course you will not see this electronic parts of the screen. So even if I change the opacity, if I lower the opacity, I make the window semi-transparent, it will look the same. So we'll not change this part. However, as I said, all these 3 coordinates, red, green, and blue, can vary from 0 to 1. So if, on the other hand, if I put here 4 ones, then we have maximum red, maximum green, and maximum blue. And if I compile it again, the result is white, maximum value of all of them. But we don't want to see the constant color. We want to visualize the function length we defined a couple of minutes ago. So I will do this. However, I will change the coordinate system first. By default, the origin of the coordinate system is in the bottom left corner of the window, and the coordinates are calculated in or measured in pixels. This is not very convenient for us, so it will be more convenient if we change the origin, if we shift the origin to the middle of the screen, and we will scale the whole coordinate system in such a way that the window will have the height of 1. So the y coordinate, the vertical coordinate, will vary from -half to half. So to do this, I will define a new variable v. This v will be a vector from the origin, from our new origin, from the middle of the screen to the current pixel. So will be the vec2. To shift the origin to the middle of the screen, I need to subtract from the current position, I need to subtract the half of the width and half of the height of the screen of the window. So I will take the position, which is this part. I will take it. I will take the x coordinate, the first coordinate, and I will subtract half of the resolution of the horizontal resolution of the viewport, 1/2 of the resolution, and I will the same resolution dot x, and I will do the same with the y coordinate. So here is a half of the vertical resolution and current. This shifts the origin to the middle of the screen, but it does not scale it. So in order to make the height of the window to be unit, for the y coordinate to vary from -1/2 to 1/2, we need to divide the coordinates by the height of the window. So I will divide it by the y resolution, by the vertical resolution of the window. So I will divide it by the vertical resolution. Of course, I use the vertical resolution because the width of the window is greater than the height of the window. Now when we have this vector, so this vector measures the distance from the middle of the window to the current position, we can display the length of this vector. So I will define y to be the length of the vector v. Of course, we need to define what y is. The length of the vector is a number, is a real number, floating point number, so the type of y is float. And now here, and we fix the color of the output, instead of 3 ones, instead of white, we will display just the value y, which is the length of a vector. So I will put here y, y, and y. And now we can check what happens if we compile this source code. As you can see, this is a visualization of the length of a vector. At the very center of the window, the distance from the center to the given pixel is 0, and which is, as we know, it is a black color. If we move away from the center, the distance increases, so the color gradually shifts from black to white. Y varies from -1/2 to 1/2, so we have some mid-gray in the mid-top of the window, and near the corners the distance is close to 1, so we have the color which is nearly white. So this visualizes our first function, the function length. So now when we have one function, we can turn our attention to the main subject of this talk, to the functional composition. What's functional composition? Functional composition can be viewed as a number of devices, of machines, of factories that are positioned one after another. So the input of the second machine is the output of the first machine. So we plug something, we feed some data to the first machine, to the first factory. This factory works on this data, produces some output, and this output is fed to the second machine, which takes it as an input and produces another output, and so on and so on. Here in this short animation that you see on screen, we have just two functions, two factories. However, there is no problem. We can to have any number of factories. Actually, we don't need to all of them to be positioned in one line. We can also consider composition of function is what is parallel, or that uses a number of different tracks that combine this original input into the final output, Anyway, we have some input, we pass it through a number of machines, through a number of functions, and we produce some output. This is functional composition. So, in short, the functional composition is when you run one function on the output of the other function. So as I said, we need more than one function to have functional composition. We need to have at least two functions to compose them together. So let me introduce a second function called step. The step function is very easy, very simple. It just outputs either 0 or 1. It outputs 0 if the input, if its argument is less than a, the parameter, a is some parameter, and it outputs 1 otherwise. So if x is smaller than a, it will output 0. If a is greater than a or equal to a, it will output 1. So we can now compose these functions together. So our input is the vector v. This v is fed to the length function that we learned first. Then we compute the length of this function and we feed this length of the vector v into the step function, and the output of a step function is what we want to show on screen. So let us see how it will look like if we write it, if we put it into our shader. So as I said, we need to feed this value y, the length of vector v, into the step function. So we need to compute step of y. I don't want to produce too many new variables, so I will reuse the variable y. So I will assign the value of step back to y, but the step function needs an additional parameter. We need to step at a given a. So let me take this parameter to be, for example, 1/4, 0.25. And let's see what happens if we now compile this function. What we obtain is a disk of radius 1/4, because if the length of a vector v is smaller than 1/4, then the step function outputs 0, the black color. If the length of the vector v is greater than 1/4, then the step function outputs 1, so we have a white color. So this way we obtain a disk of radius, as I said, 21. The radius is this parameter here. We can change this radius, and for example we can put 35 here. The resulting disk should be bigger, and if we compile it, we see that yes, it is bigger. In fact, we can even animate this parameter. I can, for example, compute the, let's say, the sine of the time, and I will compute the square of the sine of this time. If I animate it, we see that the disk pulses. So this sine function here, the square of the sine function here, means that the radius of this disk varies over time. It depends on time, so we have this pulsation here. I will stop this, and this way we see how the step function, the composition of a step function and length function produces a pattern of a disk. One disadvantage of a step function is that it has some rapid jump. It jumps from 0 to 1 rapidly. That's not what we want most of the time. So we'll introduce now a variant of a step function, which is called smooth step. It's very similar to step, however, it provides a smooth transition. It gradually changes from 0 to 1 instead of jumping rapidly as a step did. So the smooth step function is defined as you can see on the screen right now. So if our argument is smaller than a, it will output 0. If x is greater than b, it will output 1. However, on the interval from a to b, The smooth step function changes gradually in some kind of a S-shaped way by using this degree-free polynomial. So we take the relative distance between x and the two endpoints, and we compute the difference between 3 times the square of this relative distance between 2 times the cube of this relative distance. So let me just now replace in our shader the step function with this smooth step function, and we'll see how the pattern generated by our shader will look like after we introduce this change. Hence, as said, we replace the step function here by the smooth step function. And the smooth step function takes 2 parameters. I will call these parameters lowercase r and capital R, and I need to define what these capital R and lowercase r are. So this will be a constant parameter. So for example, of course the lowercase r must be smaller than the capital R. So for example, I will take the lowercase r to be 1/4 as before, as we saw for with a step function, and I will copy and paste this line to define the capital R, which must be somehow greater, so I will put here 45. And if I compile this function, we obtain again a disk, but now the border of this disk is a bit fuzzy. It is not sharp as for with a step function, because we don't have a rapid jump from 0 to 1, a rapid jump from black to white. We have a gradual change from black to white, from 0 to 1. So this gradual change causes this border of this disk to be somehow blurry, fuzzy, as you can see on the screen. So far we used just 2 functions. It was the length function and either the step or smooth step. And now we will complicate the situation a bit. We'll develop our shader, we'll use more functions we'll compose more functions together. If we take 2 step functions and we take the difference between these 2 step functions, we obtain something which is usually called a parse function. The parse function works this way. If our argument is less than a, then it outputs 0. Likewise, if the argument is greater than b, it will output 0. However, on the interval between a and b, the parse function is 1. In a similar way, we can take a difference not of the steps, but of the smooth steps. So it is a very similar function. However, as the difference between step and smooth step is preserved, so the transitions between zeros and ones are smooth, are not so rapid. So now in our shader we will replace the single step by this Parse function, by the difference of 2 steps, or actually the difference of 2 smooth steps. So all in all, our shader, our functional composition will consist of, in fact, 4 functions. We will have the length function, we will have 2 copies of smooth step, and we will have a difference. So all in all, we have 4 functions that we compose to obtain a new pattern. Let's see what we get. Hence, as I said, we need 2 copies of a smooth step. So I will take this part and I will copy and paste it again. So we have a difference between these 2 smooth steps, but we need 2 pairs of parameters. We cannot use the same 2 parameters here and here, because the result would be just 0. So I will call these parameters here R0, and this will be R1. So we have these are our R0, and I will copy these 2 lines. I will duplicate these 2 lines, copy and paste them to define R1. So we need to change the values. So for example, R0 will be 0.05. The capital R0 will be, for example, 0.15. Let me leave this R1 to be 0.25, and I will somehow reduce this to, let's say, 0.3. And what is the pattern that this shader, this code generates? If I compile this code, we see that we obtain a ring, a circular ring. Why do we have a circular ring? Because if the length of a v, length of a vector from the center of the screen to the current pixel is less than R0, then the smooth pulse will output 0. So this is the black disk inside. Then between capital R0 and lowercase r1, we have this, if the length is between these two constants, then we have this white ring, and outside the disk of the radius capital R1, so if the length of V is greater than 0.3, we have again 0, so the black. And because we are using smooth steps, not the steps itself, but smooth steps, so these transitions from black to white and from white to black are gradual, they are not rapid, they are smooth. So this produces this ring with the circular ring with blurry borders. Now I will introduce one more of this elementary function. This is a reminder of division. Most of you are familiar with the notion of a reminder of a division. So if we, for example, divide 5 by 3, the remainder is 2. So the remainder of a division is the number that is left after subtracting from our x some integral multiple of some parameter f. So if we are given some x, let's say 5, and we are given some parameter f, let's say 3, then integral multiple of 3 that fits in 5 is 1 times 3, and the remainder, the difference between 5 and 1 times 3 is 2. This is a remainder of a division. Normally we use the remainder when we talk about the division of integers. However, there is no problem to use the remainder for any x, any real x. And here, in the context of procedural modeling of producing shaders, using the remainder for any real x is far more convenient. So we know how mod is defined, but what it actually does. The mod function can be used to produce the repetitions. If we have some function, some pattern, some interesting, we generated some interesting pattern, some interesting shader, and we want to repeat a part of this pattern. So, for example, we want the part of a function, the part of a plot of a graph of a function between 0 and f to be repeated over and over again. What we need to compose our function with mod. This way, this pattern, this graph of a function, this plot between 0 and f is being repeated from minus to plus infinity. It is repeated over and over again. So we can now try to use it together with our shader. In our shader, we constructed a pattern of a circular ring. So now if we plug this mod function inside our shader between the length and the smooth pulse, we expect that this circular ring, this pattern that we created, will be repeated. Let's see if we are right. Let me enter this mod into our shader and see what the result is. Thus, we need to plug this mod function here between the length and the smooth step. So I will compute mod of y at some parameter f, and again, in order to avoid producing some additional variables, I will assign the value of this function back to y. So here we have, first we compute the length, this is the most inner function, then we compute mod of it, and then we compute the smooth pulse of it. Of course, I need to define the parameter f here, so I will do it before everything else. Float f, let's say the parameter to be 0.35. It's greater than all this already that we defined above, so it will be fine. I can compile it right now, so we'll see what happens. And we got a couple of rings. And if I want to see a bit more of this pattern, I will scale the whole screen. I will scale my coordinates a bit more, so we can see more of these rings. So we'll see that this pattern is really repeated over and over again. So I will introduce a scale. I will introduce another constant, another parameter, float scale. And I will give just 2. So I will multiply v by this scale. So I'm scaling everything twice, and as we expected, we scaled everything twice. So we shrinked our coordinate system. So we see twice as many rings in our generated pattern. The next function that I want to introduce is far more complicated than all the functions that we encountered so far. It's called Perlin noise. It was invented in 1983 by Ken Perlin, who is a mathematician and computer scientist. He graduated from Harvard in mathematics, and as far as I know, he works at the New York University as computer scientist. He invented this function, as I said, in 1983 to allow construction of naturally looking shaders, naturally looking patterns. This function is set to launch thousands of shaders because it is very useful when producing naturally looking patterns. And for this reason, in 1997, Ken Perlin was awarded Oscar, the award of the Academy of Motion Pictures, Arts and Sciences. How this function is constructed? First of all, we generate a number of random vectors. We build some finite number of random vectors. Here on screen you see just 8 vectors, but normally we have more than 8. In the original implementation by Ken Perlin, he used 256 vectors. And these vectors are constructed once and for all. They are not constructed every time we run this function. They are constructed once when we initialize our shader, before we do anything else. Before we do anything else, we also select some hashing function, some way of assigning to every integer one of these vectors. There are numerous methods to construct a hashing function. So there are ways to construct a function that assigns to every integer one of these vectors from this given set. It is important that this function should not be cyclic. So we cannot just assign first, second, third, and so on in a cyclic way these vectors. We must use some non-cyclic assignment. This is a talk, the day of pi. So we can, for example, consider a function that takes the decimal digits of the number pi, and to every integer assign a vector with a label given by the nth digit of pi. So To 1 we assign the third vector, to 2 we assign the first vector. Now we have 3, 1, 4, so to 3 we assign the fourth vector, then we assign the first vector, then we assign the fifth vector, then 9th vector, then second vector, and so on and so on. We can use the digits of pi, and this will be a kind of a hashing function. Of course, this is not a function that we would use in practice. It is far too slow to evaluate the digits of pi. In practice we use much faster function, but this gives you an impression how such a hashing function works. So now let's take our argument x, some real number x, and find its two neighbors with integral values, so the floor and the ceiling of x. These are integers, so as I said, to every integer we assigned one of these vectors. So there are two vectors in our set that are assigned to these two integers, to the floor and ceiling of x. So using these two vectors we can construct a linear function whose slope is given by this vector. So we take at the floor of x and at the ceiling of x, we take the linear function that passes through 0 at this integer, whose slope is given by this selected vector, and we multiply this function by the smooth step that we have already encountered. This way we produce two functions that on screen are marked in red and blue, and both these functions are non-zero at x. So they take some values that are denoted by these red and blue bars at x, and we add these two values together, and the sum of these two values of these red and blue factors is the value of our noise function. So the noise function is constructed this way. For every x we take these two neighbors, the two integers, we construct these functions which are called wavelets, and we sum the values of these two functions together, and we obtain the value of the noise at x. Here we can see the graph of this function on some bigger interval, and while I did it in just one variable, just using the argument which is a real number. However, we can do the same construction. We can repeat this construction in 2 or 3 or 4 dimensions. If we repeat it in 2 dimensions, so instead of 2 integral neighbors, we'll use just the 4 vertices of the square of a unit length with integral coefficients. Or we can repeat this same construction in 3 dimensions, so we will take a 3-dimensional vector v or x, whatever, and we find 8 vertices with integral coefficients of a unit cube that surrounds x. And we'll do exactly the same steps. So for every of these 8 vertices we select one of these vectors and construct these wavelets, sum them together, and we obtain the noise function in 3 dimensions. So this is how the noise functions looks like. Now what we can do. So far our functional composition was sort of linear. So the output of the first function was the input of the second function, the output of the second function was the input of the third function, and so on. However, now we will split this function, we'll make it a bit more interesting. So we'll use the noise function to disturb the position and the length of our vector v. So we will add the noise of v to v itself. So we will disturb its position, and we will add this noise of v to the length of v again. So this way we should add some noise to our pattern. Let's see what we get when we do it in our shader. Unlike the other functions that I used here, so the length, mod and smooth step, The noise function, unfortunately, is not built into the GLSL language, so we need to define it ourselves. I will not write this function from scratch. On internet you can find a number of ready implementations of this function, so I will paste here one such an implementation. This implementation is due to Inigo Quiles, and it is taken from this shader toy page. Here you can see the web address of this function. This function is not very long, is not very complicated, however it takes some time to write it. So we have now this noise function, and I said we want to disturb the pattern by adding this function both to v itself and to its length. So before we do anything else, we need to disturb the position of v. So we add to v the noise of v, noise 2 of, and we have this scale times v. This will, however, disturb the pattern too much. We need to somehow mitigate this distortion, so I will scale down this noise. I will multiply this noise by some additional parameter which will control the amplitude of this noise. So I will introduce another parameter a, so I will add to v, I will add the noise of this, and again, I said that I will do the second distortion. I will add the noise to the length of this vector. So I will change y to y plus the noise of, again, scale times v. I will just copy and paste this part here. And again, using the noise directly would introduce too strong distortion, and the noise itself is too strong. So I will scale it down again by some additional parameter, and we need to define these two parameters. So I will do it here. So our first parameter is a. This is the amplitude of the noise here. So let me take it, for example, to be 1/10. I will define the second parameter the same way, just duplicating this line. I will put b, and I will give it, let's say, 0.15, and we can now compile this code. So we see this is our shader. And if we compile it, we see that these circular rings are disturbed as we expected. So the pattern is no longer so perfect, is not so synthetic. These rings are not ideally circular. They are somehow misshaped, which is good because the natural patterns, the patterns that we meet in every day, in the outside reality, are rarely ideal. We rarely meet ideal circles, ideal squares, ideal triangles. Usually the patterns that we see in the natural world outside there are not ideal. As, for example, Benoit Mandelbrot said, clouds are not spheres, clouds are irregular. So the natural patterns are irregular, and this noise function introduces this irregularity into our pattern. Of course, these two parameters, a and b here, they control how strong this irregularity is. So if, for example, we change it, if I put here 20, 0.20, the distortion will be stronger. So the circular rings will be disturbed more. The irregularity will increase. If I change it to, say, 0.05, the rings will be more circular, more regular, and so this way we can easily control how irregular, how disturbed our pattern is. The pattern produced by our shader so far was black and white. It just consisted of shades of gray. However, we can use colors as well. So we will now introduce some color to our shader, to our pattern. To this end, we will use a function which is called mix or linear interpolation. This function is given by the formula I can see on screen right now. It is 1 minus t times a plus t times b. The nature of a and b is quite arbitrary. A and b can be numbers, they can be vectors, positions, colors, or whatever we are able to add together and compute the weighted average of. Let's see how this function mix works. If we evaluate this function at 1, then we will have 1 minus 1, so 0 times a, so it is 0, plus 1 times b, so we obtain b. So the value of our function at 1 is b. The value of our function at 0 is 1 minus 0, so 1 times a, plus 0 times b, so the value is a. So for 1, this function returns b, for 0, this function outputs a. If the a and b are the two circles that we see on screen, the blue and red circles, so for 1 we obtained the red circle, for 0 we got the blue circle, and for any value in between we obtain, well, in between position and in between color. So this mix function let us, well, as its name suggests, let us mix two colors together. So let me now use this pattern when we created these nearly circular rings as the driver for the mix function, as an argument for the mix function, and we will mix two shades of brown using the pattern we created so far, and we will see what we get this way. To this end, we replace this part where we assign the final color to our pixel by the mix function. So this will be a mix of two colors driven by this value y. I will call it, let's say, light and dark. Of course, we need to define these light and dark colors, so I will do it here before calling this mix function. So we'll define const vec. These are colors, so they need to have 4 coordinates, so this will be the light and vec 4, and we need to give 4 coordinates. For example, I will use 0.0667, 0.357, let's say 0.260, and the opacity is of course 1, because, as I explained earlier, it doesn't make sense to use other opacity here. And this was the color light, and we need to define the color dark here. These two colors are two shades of brown. Here we will have a darker color, so lower values of all three numbers. So let me give it 0.74 and 0.047, and if I compile it now, so our output color is the mix of light brown and dark brown using this pattern of these rings. So we obtain the following pattern, which somehow resembles a wood pattern. To some degree, this resembles the wood, or the natural pattern of a wood. If we cut a tree, we'll see these light and dark rings that correspond to winter and summer seasons. One last step to this first pattern when we create our first shader is of a bit different type, of bit different nature. So far we looked at the shader as a two-dimensional pattern. We treated it as a pattern generated on a rectangle. Now we'll treat it as a pattern generated in 3 dimensions. So our rectangle is no longer a part of some infinite plane of xy plane. We treat it as a face of a cube, or the cube which is positioned somehow in the space. So we look at this cube straight from some direction. We look at it along the z-axis. However, since we are working in 3 dimensions right now, we can change the orientation of the axis. So we can rotate the axis along which we generate the pattern. So we'll no longer use the same system of axes, the same system of coordinates to look at the pattern and to generate the patterns. Instead, we'll use 2 different sets of coordinates. So we can rotate the origin, we can rotate the axis for which are used, the coordinates that are used to generate the pattern, we can rotate them independently of our line of sight. So as you can see right now on the screen, this is still the same pattern. However, it is now constructed in 3 dimensions. So if we look at it along the z-axis, we obtain something on this face of a cube. We obtain something which is quite different from our original pattern. It is, well, it's some kind of skewed, it's some kind of rotated. So let me now do this inside our shader. Like with a noise function, I will paste a ready rotation code. So I prepared this code before this presentation. I have it ready. I just paste it here. The rotation is done by a function which I call rotate. It takes a vector p. It takes 3 angles, alpha x, alpha y, and alpha z, which is here. So these are the angles of the rotation around the 3 principal axes. So alpha x is the angle of the rotation along the OX axis, alpha y around the OY axis, and alpha z is the rotation around the OZ axis. Each rotation is obtained by a matrix. If you know some basic linear algebra, then you know how the rotation matrix looks like. It consists of sines and cosines of the angle. So this function basically multiplies a given vector by these 3 matrices. So how we can use it inside our shader, inside our code? We have a 2-dimensional vector here. So we need to introduce the 3rd dimension. We need to introduce a new vector, which is a 3-dimensional vector, rotate this new vector, and then drop its 3rd coordinate. So just return to 2 dimensions. So that's what we do here. So we define a 3-dimensional vector, let's call it capital V, just to distinguish it from lowercase v. It's a 3-dimensional vector obtained this way that the first 2 coordinates are just the coordinates of lowercase v, and we need to give coordinate z. Since I said on the beginning of this presentation that the y-coordinate varies from -half to half. The x-coordinates varies in a similar interval from something below -half. The aspect ratio is such that the window is broader than higher. But the x varies in a similar interval. So I will assign the z-coordinate to be again similar to be 0.5, so 1/2. And now, as I said, we need to rotate this vector. So this is our vector, and we will replace it by rotating. So we will rotate this vector, rotate vector v, using 3 angles, alpha x, alpha y, and alpha z, and now we will drop the last coordinate. We will forget about the last coordinate and we will just read the first two coordinates. So our vector lowercase v is the two-dimensional vectors that takes the first and the second coordinate of the capital V, and we forget about the last third coordinate. Of course, we need to define what alpha x, alpha y, and alpha z are. So I will do it here. These are some parameters, some floating point numbers. So, for example, the rotation around the x-axis can be 0.7 radians. The angle is given in radians as usually, and we need to multiply this line, copy it twice, and define the angles of rotation around the other two axes. So let's say, for example, I will give the following angles. So 0.7 around x, minus 1 around y, and 0.16 around z. And let's see if we got what we expect. This pattern should be rotated in 3 dimensions. So when we look at it on a flat screen, the pattern should be somehow skewed. Yes, it is. Yes, it is. So we obtain some kind of the pattern which resembles wood. So we have this kind of rings that we see in a wood. Now, when we have this shader that looks kind of like wood, we can apply it to a 3-dimensional object. If we applied it to a cube or scaled cube, we obtain something which looks like a plank. If we applied it to a sphere, we get something that will look like a wooden ball. So this is a way that shaders are used in games, in computer games, or in movies to produce the special effects, 3-dimensional graphics in movies. These shaders that are used in movies are constructed by compositing functions in a similar way as I did here. Of course, this was quite a simplistic example, the one which is easy to understand, the one which is so small that I can write it just in this during this presentation. However, the idea that I used here, the ideas that I applied in constructing these shaders, this shader is exactly the idea that is used for generating more complicated, more realistic shaders, as I said, in movies or in computer games. Let us now return to the noise function, and we'll see what else can we construct from it. How we can, other interesting patterns can be constructed directly from the noise function. So we have our noise function, and let me construct a second copy of this function, and I will scale this second copy both in its domain and its codomain. So I will scale it both horizontally and vertically. So we have our noise of x, we have 1/2 of the noise of 2x, and now we can add these two functions together. So that way we obtain a function which is a noise of x plus 1/2 of the noise of twice x. But we'll not stop here. We'll now scale the noise function 4 times, again in horizontal and in vertical directions. So we'll take the noise of 4x multiplied by 1/4, and we add it again to our function. So this way we obtain some kind of series. So it's the sum, it's a partial sum of the series constructed by taking the noise on the consecutive multiplies of x multiplies by powers of 2 and scaled by powers of 1/2. For this explanation I did it in one dimension and exactly the same way as I constructed the noise function in the first place. However, we can repeat this process in 2 or 3 dimensions. So in 2 dimensions we will have the noise of x. We will have 2-dimensional noise of 2x scaled twice. We'll have the 2-dimensional noise of 4x scaled 4 times. And we can add these 3 or more summands together to obtain a new pattern. This pattern is called fractional Brownian motions, abbreviated to FBM. If we use the pattern we obtain this way, this FBM pattern, as a height map, as the height of displacement, of the amount of vertical displacement of points of a square, we obtain something that looks like this. It's kind of a foam or maybe a terrain. However, it's not very realistic terrain, but it's kind of an interesting three-dimensional form. In the next step, I will multiply this FBM pattern by the function that we started with, by the length function. However, if we multiply it directly by the length of a vector, remember that our origin is in the middle of the screen. So at the midpoint and the center of a screen we will multiply by 0, and then the length will rise toward the edges. So this way we'll got something that will have this U shape. It's not directly what I want to get. So instead of using the distance function, the length function directly, I will use 1 minus the length. So I will invert the shape of this pattern. So instead of this kind of a U shape, I will got something that will be like a heap. So we will multiply the FBM by 1 minus the length of the vector. So the result looks like this. This is a FBM, but it falls off to black toward the edges. Again, as before, we can use it as the displacement. So we can displace the points of the unit square using this generated pattern. What we get is something that, well, sort of resembles a mountain, but it is not a very realistic mountain. The reason that why it's not a very realistic mountain is that the mountain is not homogeneous. The mountain, the characteristic of a terrain of a mountain differs with the altitude. At the bottom, the terrain of a real mountain is nearly flat. However, at the higher altitudes, near the peak, the mountain, the true terrain, is far more rough than at the bottom. So we should somehow, if we want to model a mountain using functional composition, we need to somehow model this phenomenon. So when the altitude is low, the resulting function should be quite smooth, and it should be quite rough when the altitude is high. We can obtain a non-homogeneous characteristic of our pattern if we replace addition by multiplication. Recall that we constructed the FBM function by summing the consecutive multiples of noise when we multiply the position and the amplitude by the powers of 2. We can generalize it a bit, replacing the powers of 2 by some parameters. Let L be the multiplicity, the scale of the amplitude, and S be the scale of the frequency. The reason why the generated pattern was homogeneous is that we are just summing them together. If we take the first iteration of our generation, so the first noise function, that one which is not scaled, it gives us the rough shape of our mountain. If we now multiply it by the second iteration, so the one which is scaled, which gives us smaller details of the terrain, if we then near the top we multiply the second iteration by 1, so nothing changes. So we have a quite visible changes, quite intensive changes of the behavior. But near the bottom of the mountain, we'll multiply this second iteration of noise by numbers close to 0, because we are low, we are at the bottom of the mountain. So these fine details will be scaled down, so the terrain will be smoother. Let's see if we are right, if it works. Let us compute the pattern defined by the formula you see on the screen and apply it as the displacement of the unit square. The result is almost realistic right now. However, everything is somehow mitigated or scaled down because of this multiplication of the consecutive elements, consecutive noise. Anytime we multiply by something smaller than 1, we reduce the altitude and we will never recover the altitude again. This is the reason why this mountain that we obtain right now, this artificial mountain, is not as high as the previous one. We can improve it. We can construct a bit better pattern by using the so-called heterofractal. Heterofractal was invented by Ken Musgrave, so we have another Ken here. And it is defined as a sort of a recursive sequence, a recursive formula. We start with some parameter O minus the absolute value of noise, and we square this difference. And every consecutive element of this sequence is defined in a similar way. So it has noise with a frequency scaled by a power of S. When we take the absolute value of this noise, we subtract it from O, we square it, but then we multiply it by the previous element of this sequence. So this is a kind of recursion. And now if we apply this pattern, and if we use this pattern, the pattern defined this way, as displacement, we obtain the following result, which is quite realistic. I must admit that it is quite a smart, quite a realistic, artificially generated mountain. So as you can see, by just compositing basic functions, most complicated function here was noise. All the other functions were quite elementary. It was the remainder of a division. It was the length of a vector. It was the step or smooth step, which was cubic polynomial. We obtained something that is quite realistic. It's no longer a synthetic pattern. It looks quite convincing, like something that we encounter in reality outside. I will, on the end of my talk, I will show you some examples, some more advanced examples constructed by other people, by people more talented than myself. For example, the following mountains were generated in a very similar way, using the ideas I presented here. The author of this picture is Levis Nin. Here is another example by Nathaniel Doldersam. And here is even a more advanced example by Inigo Quiles, which both the landscape behind the temple and also the temple itself. The temple that you see on the screen is completely generated using shaders. It's not modeled by hand, it is fully generated in a code. It is coded. It is directly written shader toy, as you can see here directly in the shader toy. Actually, on YouTube you can find a video by Inigo Quiles when he shows how he did this picture. Another picture by the same author, Inigo Quiles, a snail, which is also generated completely on screen, completely written as a code. It's not modeled by hand, it's generated here. You can see the code of this shader, and this code generates this picture. That is all. Thank you very much for watching this video. I hope you enjoyed it, and this way you learned how a mathematical notion of functional composition can be used to obtain the patterns that are very, very far from mathematics. Actually, or apparently far from mathematics. The patterns that looks quite natural, that resembles natural phenomena, but they are still obtained by the just compositing functions. Thank you very much.